So this is my dad, and he's a pretty good dad, but every so often he does this, or this, or this, and I want to hit him in the face with a pie. So that's what we're going to do today. The only problem, I'm not the most athletically gifted. I tend to throw it too short, or too long. So today, we're going to use physics, more specifically, kinematics and projectile motion to help me out. Kinematics is a form of math that describes the motion of moving objects, and projectile motion is the study of those objects where the only force acting on them is gravity, like a bullet or other projectiles. So you can see how that relates to our pie, because when I let go of the pie, it's all up to the big guy. I mean the Earth. Before we can get to pie throwing, we need to do some background. When we're doing our math today, we'll be dealing with scalar quantities, quantities with only magnitude like time, and vector quantities, which are quantities that have a magnitude and direction, like displacement. We'll mark those with an arrow above them, like this. Those are where we get to diagrams like this, our Cartesian plane with a vector arrow. Now we understand that these arrows are always vectors because they have a direction and magnitude. We can also write vectors like this, or this, but for simplicity's sake I like the second one, so that's how we'll be drawing them for the rest of the video. Now back to physics, and how physics is going to land a pie in my dad's face. Our pie is a moving object, and it's going to be experiencing a constant acceleration, which means that we can use the 5 motion equations to describe its movement. Specifically these 5 motion equations that each relate 4 of the 5 following variables: time, displacement, initial velocity, final velocity, and acceleration. These 5 equations are set up in a way so that each equation only has 4 variables, which means that if I have 3, I can solve for the final. Let's look at this example. A car traveling down a highway suddenly comes to a stop. It takes the car 90 meters to stop, and this happens over 6 seconds. What was the initial velocity of the car before braking? Now, it may seem that this question only gives us 2 variables since there are only 2 actual numbers given, but it actually gives us 3. The wording of the question gives us our third by telling us that the car is coming to a stop. If at the end of the question the car is still, then final velocity is 0. We know that we're finding initial velocity, so we need to use the equation that doesn't require acceleration, since that's a variable we neither have nor want. We use equation 2, and subbing in our numbers, we get a value of 30. Therefore, the car was initially traveling at 30 meters per second, or 108 kilometers per hour. Now I hear what you're saying. That's all fine and dandy for a 1D problem, but our pie is going to have 2 dimensions, right? Absolutely. Which means that to solve this problem, we'll have to use components, which raises the question, what are components? Using components basically means breaking a vector or vectors into its x and y values, or components, using trigonometry, and then adding them back together with more trigonometry. Let's look at another example. Let's say that we have a blue jay, and this blue jay travels 15 meters east 35 degrees south, and then 8 meters west 70 degrees south. Where does this blue jay end up? Well, let's split up that first vector. We can see that its x component is adjacent to the angle, and that's since the 2 components make a right angle here, we can say that the x component of this vector is equal to the vector times the cosine of this angle. We can then also say that the y vector is 15 times the sine of 35. But it's important to notice that this component is pointing down, and since I like directions up and right to be positive, we'll put a negative sign on anything that's down or to the left. We can do the same process to our second vector, and now we're ready to add the two to each other. We add the x and y values to each other first, and that gives us this triangle, with angle theta and vector r. This is another right angle triangle, so we can use Pythagorean's theorem to find r, and the inverse of tangent of the opposite over the adjacent to find theta. We get a final displacement for our blue jay of 19 meters east, 59 degrees south. Okay, surely, it must be time to throw a pie in my dad's face now, right? I can use the motion equations, I know how to break vectors into components. What else could I possibly need? Well, like I already said, our pie is going to be a projectile, so we need to learn a couple specific things about projectile motion. When an object like this ball is experiencing projectile motion, that motion is going to have horizontal and vertical components. Something cool about these components is that they're actually independent, only sharing the same time. You can see this by holding 2 identical coins in your hand, dropping one coin and tossing the other in a horizontal direction. The coins will hit the ground at the same time because they have the same vertical motion components. Now, if you remember, a projectile is an object where the only force acting on it is gravity. Since gravity only works towards the Earth, or in the vertical direction, the horizontal component of a projectile will have a constant velocity. This means that we can use a simplified formula for this component. Now that we know that, we can finally apply this to hitting my dad with a pie. My problem is that I keep over or undershooting, so I need to find an angle theta that will help me land the pie right in his face. I know that the displacement between me and him is 2.5 meters in the horizontal direction and 0.56 meters in the vertical, that the time of flight is 0.7 seconds, and that the pie's acceleration is going to be the same as gravity, or 9.8 meters per second squared. All that's left is the pie's magnitude of velocity, or speed, and the angle of theta of its velocity, which is what I want to solve for. I can determine the speed at which I can personally throw a pie by throwing a pie horizontally and tracking how far it goes in its time of flight. This works because when the initial vertical velocity is 0, the initial velocity is equal to the initial horizontal velocity. Since the initial horizontal velocity is equal to the horizontal displacement divided by time, my initial velocity for pie throwing is 4 meters every 0.9 seconds, or 4.44 meters per second. Now that I know that, I can use it for my initial speed for the pie destined for Dad. Breaking that pie's motion into horizontal and vertical components, I can rearrange either equation and solve for theta. Substituting my values in, I get an answer of 36. So if I want to hit my dad in the face with the pie, I need to throw it at an angle of 36 degrees. I can check my answer one more time to make sure that I'm about to do it right using the other set of equations. And let's do it. Now if only I could throw that accurately. Hey, easier said than done, am I right?